Okay, so this chapter is about components of thermal systems, solar thermal systems. So this is more of a practical knowledge about the components of solar thermal systems, how those uh, the basic working principles, their types, their typical materials which are used, and what are the purpose of those components. Right, so all will be briefly discussed in this chapter. So it's mainly theory, very little part of numerical is involved in this chapter. So I will try to go through it quickly so that we can finish it in 1 or 2 weeks. And we can quickly go to the next most important chapter of this course, the thermal analysis of solar thermal system or solar thermal collectors. Okay, this chapter is again covered from different books, but mainly I use this book, right? Planning and installing solar thermal systems, right? So majority of the data is taken from this book. Okay, so now let's start this chapter. Now, components and subsystems of a typical solar thermal installation is shown in this picture. So what you see here, it's a kind of a solar water heating system is shown. So here is the solar collector, which is the main energy generation device, which is absorbing that solar radiation, right? And we just covered in chapter 1 and 2 how to find out this incident radiation. And the part which gets absorbed here, then this absorbed part goes to the fluid. Now this fluid, for example, entering here at low temperature and leaving at a higher temperature. So this is the component 1, solar collector. There are many types of solar collectors which we will see in this chapter. Then you see there is a pump which is making this fluid to flow. And for the storage, there is a storage tank. There is a heat exchanger you see here. If this fluid and this fluid inside this tank, they are different, then we have to use a heat exchanger. There is pump, of course, and this is expansion valve or expansion chambers actually. So this one, this is called expansion chamber. So we'll see what are the what is its function later on. Then you see backup heating source, right? And controller. There is some kind of controller which is making this pump to switch on or off according to a defined criteria. For example, whenever the temperature in the collector here, for example, at the exit, this temperature TO is higher than the temperature in the tank T of storage. So whenever this TO is bigger than T storage, only then pump should switch on, otherwise pump should switch off, right? If the temperature during night time or when there is no solar radiation, so this temperature TO may be equal to or even less than T storage, then pump should not be running. So that's why to control this function, there must be a controller also. So these are the typical components of any solar thermal installation: collectors, storage tank, heat exchangers, pumps and expansion chambers, controllers, and other components load all those pipes, valves, uh, different types of valves which are used. So those come under this category of other components. Okay. So the main components are shown here. As I told you, what is the function of a solar collector? So that must be mounted on the roof outside to convert the solar radiation, solar light into heat, right? So collector is actually a link between sun and our useful uh, application, whatever it is. Here, the application which you see, it's a domestic water heating. Now we can classify these solar thermal systems mainly into two major categories. One is forced circulation. So this figure which you see here, it's a solar heating installation which is providing hot water for the house. Now it is a forced circulation because there is a pump which is making this fluid to flow. And also this system, this solar loop is closed loop, totally closed loop. And also it is, you can say it is an indirect type. Yep. This system which we see here, it is an indirect, closed loop and pumped system. Closed loop is clear. This solar loop is not open to ambient. That's why we call it closed loop, right? This one. Indirect means there is a heat exchanger. It's not directly mixing with that pot water. So here we may be using a different fluid, right? Some kind of antifreeze. Maybe there is, if we are using that solar system in a location where you may encounter freezing temperatures during the night. So the normal water may freeze. So that's why we may use an antifreeze in this loop. So, and this is a normal water which we need for other usage. So now the two fluids are kept separated from each other using that heat exchanger, right? That's why it is called indirect. So now every term is clear. This system, typical system which is shown, it is indirect, closed loop and pumped system, right? The fluid, it's separated. So I told you we may use antifreeze as some anti-corrosive agents we may be using in this particular fluid, right? So that's why it has to be kept separated from the normal water which we are using here, normal water for domestic usage. Okay. So this system is a pumped circulation because there is a pump, right? So we can keep the storage tank inside somewhere in the basement because of the pump, we can make the fluid to flow anywhere, right? So that's why majority of the system components are inside and outside is just a solar collector, right? So because the storage tank is inside, so that's why the thermal losses to the ambient are less. Low thermal losses from the storage tank and also from these pipes because those are not exposed to cold ambient, right? Auxiliary system is also installed in series with this pot water, right? It could be an instantaneous water heater, right? So it can increase the temperature, the desired temperature if it is not reached here through that solar system. So it can increase the temperature immediately. So in most of the solar water heating system, this is the most commonly used solar thermal system. This forced convection, indirect, right, and yeah, system. The other one, which you see here, that is natural circulation, or that is also called in solar field. This term is very commonly used. That is called thermosiphon. Thermosiphon means in this particular system there is no pump. Everything is by gravity or density. But in this particular system now, you cannot keep the solar collector inside or anywhere. You have to keep that solar collector at the top of the collector, right at the top of the collector, to have that natural circulation. Natural circulation means the coldest portion of the water will always be at the bottom of that tank, and that cold water is flowing towards that collector. In the collector, because of this solar radiation, it will heat the absorber plate and the pipe, and the fluid which is present in those pipes connected to that absorber plate, that will be heated up. As this fluid will be heated up, it will start to rise up by itself, because as the temperature increases, density drops. So when the density drops, the fluid starts to move upwards. So there will be a natural circulation setup in the entire system. The cold fluid is coming down by gravity, and the hot fluid, because its temperature is rising by absorbing solar radiation, so density is dropping, so it will start to rise up. So cold fluid is pushing from the bottom, and hot fluid is going up because of the drop in density. So natural circulation will be set up in the entire system, right? So the basic principle is that the hot water, it rises. When you heat the water, it will start to rise. And these are called thermosiphon systems. So storage tank must be outside in this particular system, and it should be above the collector. So now there will be a circulation. It's all natural or thermosiphon. So this particular system, of course, it's very advantage to use such systems because it's much simpler, right? Compared to the previous one, it's also cheaper. There is no pump or fan required, right? But there is also an issue now. The storage tank is outside, right? Storage tank before, in the previous case, it was inside, but now storage is outside. So you have to make a heavy insulation for that solar collector, because it is placed outside, there will be more losses. And also there is no controller required, because everything is by buoyancy or gravity, right? So every movement here is by density or gravity. There is no control about the circulation of the fluid in these systems, right? So there could be an issue of overheating if you are not using that hot water during the daytime, and there is clear sky. So then this fluid will maybe overheating here, and when the fluid starts to overheat, then it will start to damage those materials of construction, right? So that could be one disadvantage, right? Because in case of pump system, we can make this pump to make this fluid to move throughout, and all the time some cold and hot fluid is mixing with each other. But here it's there is no such control. Okay. So these are some advantages and disadvantages of the system. Just read it by yourself. Okay, it's not that difficult. Okay, so here you see another diagram of a forced circulation. So here you are using some engineering symbols in this particular diagram. So here you see solar collector. So it's the main components we just saw before, but there are some other components. For example, here you see a check valve. So, because during the night time when there is no sun, we do not want this cold fluid should start moving towards the uh, collector during night time. The fluid which is present here, it will start to move backwards by gravity towards the storage tank during night time or when there is no sun. So that's why we have to use a check valve to prevent that flow in the opposite direction. So this check valve will make sure that fluid is flowing only in this particular direction. There are other safety valves. There are a manometer to measure pressure if if we are interested, because when the steam starts to produce here, so it will start to increase the pressure. Also, there are thermometers to measure the temperature at the inlet and exit of that solar collector. There is this purge valve that is used to remove the air particles in that fluid flow. So it is normally installed at the top of that circuit. so that whatever air particles are there, those should be removed with the help of that purge or air vent, it is also called. So this is normally used in these solar thermal systems. Right, so there is that expansion chamber, which we will discuss later on also, but here the purpose I can briefly tell. If the system is overheating, right, there is we are not taking that heat out, so the system starts to overheat. Overheating means the fluid starts to expand, so we should give some extra space for this fluid to expand in that particular case, right, when there is no water taken out, hot water taken out. So this fluid which is present in this loop, it starts to overheat. So when it starts to overheat, it tries to expand. So we should give this extra space for expansion. So that's why this expansion chambers are also installed. There you see a flow meter to measure the flow. Here is the shut-off valve. If you want to separate this system from the storage tank for maintenance purpose or cleaning purpose, so that's why we can use these shut-off valves to completely stop the fluid flow in that loop, right? So yeah, so there is also a safety valve. If the pressure in the system becomes too high, right, then this safety valve will make this fluid to open, to leave from that system, right? So the safety valve. So all of these we will learn by one in this entire chapter. Okay. So these components are again shown here, right? You see collector, tank, pump, piping, expansion valve, air vent, and there are many different types of valves which are used, and of course temperature and pressure sensors to measure its performance, the real performance. So this is a forced circulation, same we can see here. For natural convection, now there is no pump, but still there is an expansion valve. There is that safety valve, right? In case of overheating, it may open and make the fluid to leave, right? So here is that cold water coming from your main tank, for example. This is our main storage tank for house, home, or offices. That cold water is entering into this storage tank, hot storage tank, and hot water is leaving from the top to the home. So here we may be using a pump, but within that solar loop, there is no pump. So that's why it is a natural circulation. So here you again see the same purge valve to remove any air particles which are present in that loop to leave from here. All right. So the rest is the same thing. So here again you see a check valve, right? A filling valve to fill that fluid in that entire loop. All right. Okay. Now one by one we will go through each component, but the most important component in the solar thermal system is of course this one, solar collector. So next we shall study theoretically about this solar collector in more detail, right? So now let's focus on what is that solar collector. So here we see different types of solar collectors, solar thermal collectors, which are used in solar thermal systems. What are these? They are heat exchangers, right? All of them. They are actually particular type of heat exchanger. What they are doing, they are converting solar radiation G into heat, right? So radiation is converted into heat using that heat exchanger, which we call it as solar collector, right? So these solar collectors, which are used in solar thermal systems, those can be classified into two major categories. What are two major categories? Here, those are mentioned: non-concentrating or stationary type. Second major category is concentrating type. So here we see this non-concentrating or stationary. No, stationary means they are not tracking, they remain fixed on their position. All right, so for example, this one is a flat plate solar collector. This one, which you see here, that is called evacuated tube collector. So we shall be learning about them in a moment. So these two are a non-concentrating or stationary. They are not tracking, they are not concentrating. They are directly absorbing whatever radiation is present. It's beam or diffuse or ground reflected. All of them can be intercepted by these collectors, flat plate and evacuated tube collectors. Okay, they can absorb beam, diffuse, ground reflected, whatever type of radiation which will reach on their surface, they can absorb it. The second major category is this concentrating type of collector. So here you see different types of concentrating collectors. These are called parabolic trough, these are heliostat, these are parabolic dish, these are heliostat reflectors. Okay. So a large number of mirrors. So again, we shall see one by one each of them, but all of them, they are concentrating solar radiation from a larger area to a very smaller area, from a very larger area to a very smaller area. Same here. This is the large mirrors which are receiving the solar radiation. They are reflecting it. Now they are converging it to a smaller area. So here is the receiver. So here is the receiver or absorber, and this part is reflector or aperture. Okay, this one. Same here, these are reflectors or the apertures, and this is the receiver where the solar radiation is made to concentrate. So a large area is receiving solar radiation, a aperture, but a very small receiver area is absorbing the same radiation. So in these type of collectors, they are only mainly dependent on beam type. Such concentration at a defined angle we can only achieve for beam radiation. So their performance is poor for diffuse or ground reflected radiation, because diffuse and ground reflected radiations, they are not coming at certain defined angle. Their angle is different or changing throughout the day, and we cannot say that diffuse radiation is reaching on one particular angle. That is one particular assumption which we use in the previous chapter, but actually they are coming from everywhere. So these type of concentrating collectors, they have one limitation or restriction, that those can only be used for beam type radiation. But they can give us very high temperatures, because we are concentrating a large area on a very small area. Whatever radiation is falling in that large area, now it is made to concentrate on a very small area. So that's why in these in these types of solar collectors, we can achieve very high temperature, because we have a very small receiving area and very large concave reflecting area, right? But here these are only for these ones, fixed type and non-tracking. Their advantage is that they can absorb all beam, diffuse and reflected. But here in this case, the absorber area or receiver area and the reflecting area or the aperture area, both aperture area and absorber area are same. Here, aperture area through which radiation is entering, for example, in the case of dish, this area, this entire area, this is the aperture area. But the receiver area is very small, or absorber, we can also call it absorber area. So these collectors can give very high temperatures, but here we cannot get very high temperatures. Okay, so these are the two major classification of solar collectors. Now we shall go one by one through these collectors. One by one, we will learn their working principle. So first of all, let's start with the non-concentrating type solar collector. And in non-concentrating type solar collector, there are three major types. One is flat plate solar collectors. Second is stationary compound parabolic collectors. So we'll see in a minute. And the third one is evacuated tube collectors. So in non-concentrating type, these are the three major types, which falls under the category of non-concentrating collectors. So the simplest type of solar collector is the flat plate type solar collector, right? Here are the main components of that flat plate solar collector are shown, which I have been explaining in the previous two chapters also. So here the major main components are shown. The glazing through which solar energy enters. Then, because it's a side view, let me show you the cross-sectional view which I have been drawing before. So the first of all, there is glazing, this one. Next is absorber plate. So here is this is absorber. Then there are riser tubes. Now tubes can be welded under these absorber sheet, or in some cases they can be welded over the absorber. These are the tubes in which the fluid is flowing, right? So these are also called riser tubes. So if you see in 3D, so it will be something like this. So here are the tubes. So if you see from this side, this view is shown here actually, a tilted collector. So this riser tube is shown like a long pipe here, this riser tube, right? And here the absorber plate is at the bottom, riser tube is at the top. Okay, it could be at the top, it could be at the bottom. Both designs are used. Okay, so the same portion, this riser tube, which is welded to the absorber, is separately shown here. So this riser tube, the cross-sectional view, which is attached to this absorber. This absorber is a flat plate, which is acting like a fin. So from your heat transfer, you would know what is meant by fin, right? So these riser tubes are normally welded to this absorber plate, flat plate, right? So maybe welded or maybe bonded with some material. So there could be actually there's no space which is shown here. Actually, it's showing it is kind of a bond is there between the riser tube and that flat plate. All right. Okay, what else? At the bottom of that plate, there is insulation because from the top, solar radiation is falling and getting absorbed here. And that is what we covered in first two chapters. Now, after absorbing, what happens? The temperature of this absorber plate will increase and there will be a heat transfer from the absorber plate to the riser tube. And inside the tube, there is a fluid flowing. But ideally, we want all the heat of this absorber plate should be flowing towards the tube, right? Whatever heat is absorbed here, that is S. Now it should be flowing towards the tube. So here is the heat which we want to flow. But some of the heat will go back into the ambient from the top, and some of the heat may be lost from the bottom of that absorber plate, right? So at the bottom we use some kind of insulation to stop this heat loss from the bottom. Okay. So that's why there is always an insulation used at the bottom side of this absorber plate. Okay. So now this glass, this absorber with the tube welded, and this insulation at the bottom and on the sides, all of it is housed in a casing. So here you see an outer casing. It could be a wooden casing, or it could be some other plastic or aluminum of any type. So that is a casing in which it is housed, and here you see that those gasket to seal it properly so that no outside air will be entering into that portion to 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 cool it, right? So that's why these gaskets are used. Now, what is this header? Because these riser tubes, if you see these riser tubes, if you see from the top, you will see these riser tubes. They are connected to a header in a bigger pipe. So fluid is entering into the header. Now it is divided into these tubes, riser tubes, which are connected to that absorber sheet. And so there is an inlet header, there is an outlet header. So here, that's why you see header, a bigger pipe at the top and also at the bottom. So fluid, for example, entering from here, divided into a number of riser tubes and then collected here and goes out from here. So this is header. Okay. So we'll see some more pictures to clarify all these. So these are the major components. Now let's see what are the functions of those components. One of the most important thing is this glazing, right? And we solved that glazing in chapter 2, the reflection, absorption, and transmission losses, which we calculated for that glazing. But we should know why we are using glazing, right? So in solar thermal systems, there will always be a top surface, which is a glazing, which is mainly made up of some transparent material or semi-transparent solid. And in most cases, it is a glass. But in some cases, you can also use plastic, transparent plastic. So what is the role of that glazing or plastic? What they do, they allow the solar radiation to pass through, right? So the purpose of this glazing is to allow the majority of the solar radiation. But then there is a second major function of that glazing, that whatever is passed, now it will be finally absorbed, right, onto that absorber plate. Then absorber plate will start to emit radiation. But this glass cover will block this radiation emitted by the plate, because that is of long wavelength radiation. Just a minute. Okay. So that is the major purpose of this glass cover. It will allow the solar radiation to pass through, but it will block the long wavelength radiation emitted by that absorber plate or that pipes, right? Because these absorber plate or those pipes, their temperature is much lower than solar radiation, than the sun. That's why they are emitting long wavelength radiation. So these glass has this property to block these radiations, long wavelength radiation, but they will allow the short wavelength radiation to pass through, majority of it, the transmittance which we calculated. So that's how a greenhouse effect is created in this portion. So that is the major advantage of using a glass cover, right? Then after glass cover, we see the absorber plate. Now, what is this absorber plate? Those are normally metal sheets which are painted with some coating, and this should have high absorptance, which we also saw in previous chapter. That will trap or absorb that heat, soak up that heat. Then, so this plate is normally coated with a material like black paint or any other material which should have high absorptance but low emittance, right? So normally we paint this black sheet with high absorptance and low emittance surface so that it can absorb maximum solar radiation, which is finally reaching on that surface, right? So this absorber plate should have high absorptance. This glazing should have high transmittance of solar radiation, incident solar radiation. Insulation, as I already explained, it is provided at the back side of the absorber plate to decrease the heat loss from the bottom, right? Because ideally we want all of this heat which is produced here or which was produced due to the absorption of solar radiation, that should be transferred to the riser tube, the fluid which is flowing in these riser tubes. So we need to prevent all other losses of heat. So one of the losses would be from the bottom side of that plate. So to prevent it, we use insulation. Then those are the riser tubes, because these are the vents or pipes which are welded or bonded to the absorber plate. And in that pipes, the fluid which we want to heat up is flowing, right? Here is the casing, the outer casing in which the entire structure is housed, right? So here is the same working which I already explained. So here is, let's see again, here is the incident radiation in the visible range. Majority of it is in visible range. A part of it will be reflected. The rest will be transmitted, and we know how to calculate. And finally, it will be absorbed on that absorber plate. Now this absorber will start to emit, but this emitted radiation will be blocked. So here is the emitted radiation by the absorber, but it's not in the visible range, that is in the infrared range, non-visible range. So this long wavelength radiation will be blocked by that glazing or glass. So here is that absorber plate with some type of coating. So we'll see what is meant by selective coating later. So this coating has this ability to absorb maximum and emit minimum. So here is the fluid carrying passage in which the fluid is flowing, and this heat will be transferred from this absorber to this fluid. Here is the insulation, right? There will be heat losses from the top of the absorber by convex, because here there is a air trapped, outside is also air. There is this glass cover, so there will be a heat loss back to the ambient by convection, then conduction, and then again convection, and also by radiation, right? Because here this plate will be at high temperature, for example TP. This is ambient, which is at low temperature, right? Ambient is not only on the front, also at the back. Ambient is everywhere. So from the top there will be heat loss, and also there will be a heat loss from the bottom. So we try to minimize this heat loss back to the ambient, and that's why we use glazing from the top side and insulation in the back side. Okay, any question here in the basic working of that solar thermal collector? That is also explained here. Now we can see some more pictures to clearly understand what is happening. So here I was telling you that header pipe in which the fluid is entering, and these are the riser pipes, right? Outer casing is shown. Here is the top glazing or glass cover, at the bottom insulation. So here is a 3D view, which and this is the absorber plate over which those pipes are bonded or welded. So this flat plate solar collector, the arrangement of these tubes could be in this manner or in this manner. This is called header and riser type design of flat plate collector, and this is called serpentine design, right? In this design, as you see, there is one header at the top and fluid is distributed in these riser tubes, and on the other end there is another header. So that is called header and riser type of solar collector. Here issue is that the fluid will be distributed, but it will not be distributed evenly. All right, so some tubes will be receiving higher flow rate, some will be lower flow rate. That's a complete different topic to understand the flow distribution. Okay, but in these header and riser types, there will be uneven flow distribution. Each pipe will not be receiving the same amount of m dot, because here, because of this design, header and tube design, the the fluid is not evenly distributed. So that's why we have another design. This is serpentine. Look here, the same mass flow rate which is entering, and now the same mass flow rate is made to flow like this, in this manner. This is called serpentine type, right? In this case, the total m dot is divided into m dot 1, m dot 2, m dot 3, depending upon how many pipes we have, and all of it will again combine in the main head. But in this particular, in the serpentine case, the same mass fluid which is entering here, the same will be leaving here. There will be no distribution. So there is no issue of this uneven distribution. So these are the two major types of solar collector based on this fluid flow within that solar collector, right? So one is header and riser type, other is serpentine or serpentine. I don't know the exact pronunciation. Okay. Okay, so it is explained here. Just read it. It's not that difficult. Here you see the same header and riser. The actual typical picture is also shown. Now this absorber plate, it could be one single sheet and pipes are welded, or it could be, look here, it could be small strips. This absorber could be small strips, and each strip has one pipe welded. So here are small strips of absorber sheet we can see, and at the bottom insulation is also shown here. Here is the header pipe. All right, so this absorber plate can be a single sheet like here you see, on which all the risers are fixed, or each riser can be fixed on a separate small absorber sheet, which is also called fin. Okay. Purpose of cover I already explained. So it will allow the short wave radiation to pass through, and it will block the long wave radiation which is emitted by that absorber, and that will create a greenhouse effect. So these flat plate solar collectors, they are inexpensive to manufacture. These are the most simplest type of solar collectors which we can have. And here you see some actual picture of a flat plate solar collector installed, and look, all of them are tilted at certain angle beta. All right. So how to select this beta, we already studied in chapter 1 and 2. And they can collect both beam part and diffuse part. So all of those points we have already discussed, right? What should be the optimum tilt angle? That is also we discussed in chapter 1, right? So here is a typical rule of thumb. It should be 10 to 15 degree more or less, depending upon application, and depending upon latitude. Application means if it is an application for winter or if it is an application for summer. Winter application or summer application. For winter application, sun is down, so you have to tilt that collector 10 to 15 degree higher than latitude. So it should be 5 plus beta. And for summer application, sun will be more up. So this tilt should be, sorry, this 5 plus, it was del, I remember. This is beta, 5 plus del. So in general, we can say 5 plus this 10 to 15 degree. All right. Otherwise, exact del on that day for which we are designing or for month. And for a summer, it should be 5 minus del, if you remember. So 5 minus 10 to 15 degree, right? That is the collector tilt, this one. That's what we already covered in chapter 1. All right. Latitude plus 10 or latitude minus 10 to 15 or plus 10. So this is a rule of thumb for this beta or collector tilt. All right. Okay, these are some common points. It's not difficult, just read it. We want that these solar collectors should have a long life. It means they should be able to withstand solar sun's ultraviolet radiation. Those materials should be able to withstand or bear that ultraviolet. And also there should be no corrosion and clogging because of acidity or alkalinity or hardness of that working fluid. Whatever working fluid we are using, in normal cases it could be normal water or it could be water plus some antifreeze mixture, right? So whatever type of fluid, or it could be in some cases we heat some oil. So whatever working fluid we are using, it should not corrode or it should not block the passages. Freezing of working fluid, we should be careful about that. Any type of dust or moisture which will be produced here, right, on that glazing, right, that should be avoided. Otherwise it will degrade the performance of that solar collector, right? Because of, and this glazing should be strong enough to bear rain or hail or these storms, something or other reasons, right? Similarly, glazing materials, that transparent cover which we are using, it should have high transmittance, low reflection, clear. It should be protected from the cooling effects of wind and convection, because if outside there is wind, it's cooling, it's cold wind flowing. So here you have air inside, because in between glass cover and that absorber plate, here we have air. If cold wind is flowing outside, so that will make this moisture present in that air to condense on the surface of that glass, so that not only on the inside, maybe outside also. So because of this condensation, the transmittance of that glass cover is affected, that will reduce. Okay, so there should be a protection from moisture. So these are general theoretical points which you can read by yourself. Okay, I will just explain the major points. The rest is not that difficult. The type of glass which we should use, it should have 90, ideally it should transmit 90% of the incoming solar radiation. And what type of glazing is best suited? It is normal glass. Okay, we can use plastic fins, but plastics, their issue is that at high temperature they may degrade, right? But those are inexpensive compared to glass. And also transmittance of glass, as we discussed in previous two chapters, they vary with angle of incidence. As the angle of incidence is changing, this transmittance does not remain constant, it also changes. All right. So we should use a glass with low iron content, which should have high transmittance, right? Approximately in this range. This is the tau value ideally we are looking for. And they should block the radiation emitted by the absorber plate. So if this absorber plate will be emitting radiation in this range, so they should be able to block this one and transmit the solar radiation, which is a smaller range than this one. All right. Okay, the rest, it's not difficult, just read it by yourself. So plastics can be used because plastics, they are not broken by hail or stones. That is the major advantage. But normally their transmittance is less than glass, plastics. And also their temperature limitation. They cannot sustain very high temperatures. Okay. Okay, so then we'll continue our discussion about absorber. Okay, so from this point, I will continue this theoretical part, so in the next lecture.